Everyone, this will be a brief presentation on our integrated project covering reaction engineering 1 and separation process 2 for January 2020 semester. Let's start off with the reaction engineering 1 introduction. Now, these are the equipments involved in the production of hydrogen, which is a mixer where steam and methane is inserted to come off as reactants, and the reactants are channeled to a steam methane reformer followed by a water gas shift reactor. The two primary reactions involved in the production of hydrogen is the steam methane reforming (SMR) and the water gas shift (WGS). Now, SMR and water gas shift has to be done under catalyst, which is 0.48% rhodium supported on alumina and 50% copper oxide supported on zinc oxide and alumina, based on the literature study that was done by us. And both of these are catalysts, so the best reactor to be used will be packed bed reactor (PBR) because this is one of the basic reactors that can accommodate catalysts. Now, this is the basic flowchart of the production, and the hydrogen to be produced is 30,000 tons per year, which is equivalent to 6,903 kilomoles per hour. And under specific conditions, which is a steam carbon ratio of 5, conversion can be assumed to be 91% for SMR and 63% for water gas shift. Now, this is the stoichiometric balance for the production, and substituting the final value of hydrogen 6,903 kilomole per hour into the 3x plus y and using the conversions where appropriate, we can find all the final molar flow rate to be as following. Next, we'll talk about the SMR reactor sizing and conditions. So the formula to find the weight of catalyst in a PBR is negative FA naught dx over RA prime, which can be converted to V equals to negative FA naught dx over RA using the two equations, which are RA reaction rate per volume is equals to RA prime reaction rate per gram catalyst times by the bulk density, and the weight is equals to the bulk density times by the volume of PBR. Now, SMR is CH4 plus H2O, which will be converted to CO plus 3H2. And the assumptions done for this process is that the side reactions are eliminated and it is made irreversible, which will be explained during the reaction conditions. So the reaction rate, the rate law is given by 0.22 PCH4, which is from our literature study, and we can convert it to 1871.4 CCH4 naught 1 minus x over 1 plus epsilon x using the ideal gas law, and the epsilon, the expansion factor, is found to be 0.33. Now, substituting both these formulas into the volume of PBR, we can find that the volume required is 2000 dm cube, which is equivalent to 2 meter cube. So this is the best sizing for the PBR, where the PBR will have a 1 meter diameter and 3 meter length. The mass of catalyst in SMR reactor will be the bulk density times by the volume, which is around 5,600 kilogram. And the best temperature to be used is 750 degrees Celsius, and the pressure will be 0.5 bar. This is because the SMR is an endothermic reaction, and conducting it in a high temperature will eliminate the reversibility of it. And SMR is also known to have a side reaction, which is the Bodart reaction, which is exothermic. So having a high temperature will minimize it and eliminate it as well. The SMR reaction is also known to have methane cracking as one of its side reaction, which is eliminated by supplying steam in excess. And the pressure has to be maintained very low because according to La Chatelier's principle, the product has a higher mole compared to the reactant. So the pressure should be maintained to be lower so that the equilibrium is shifted to the right.
Hi, my name is Fazreen Elyana, and I will continue the presentation on reaction engineering part, and I'll be focusing on water gas shift reaction. So as presented before from previous presentation on SMR reaction, we know that SMR reaction would produce most amount of hydrogen in the production unit. It used methane as the raw material and water supplied as steam to produce carbon monoxide and hydrogen. This is a good source of hydrogen, but it also releases carbon monoxide, which is very harmful to the environment. To counter this problem, another reactor is placed after the first reactor, which is the water gas shift reactor. So the equation for water gas shift reaction is CO plus H2O will be producing CO2 plus H2O. So the objective of WGS reaction is to minimize the release of carbon monoxide to the air and produce even more hydrogen, which would increase the overall yield of the production plant. The reaction conditions for WGS reaction is first, it needs to be carried out at low temperature to make it irreversible. This is because the reaction is exothermic, and by lowering the temperature would shift the equilibrium towards the right according to the L'Hopital's principle. And according to our source, which is Noor, Key and Chen, the optimal temperature for a low temperature using WGS, using the catalyst 50% of CuO supported by ZnO supported by Al2O3, is between 180 degrees Celsius to 200 degrees Celsius, and therefore for packed temperature is set at 185 degrees Celsius. Next, steam is also supplied in excess to increase the conversion of carbon monoxide to carbon dioxide, and this will increase the production of hydrogen. The reactor is also made isothermal by using a water jacket to cool the reactor from the heat released from the reaction. And since both of the product and reactant sites have same number of molecules, the pressure is set close to atmospheric pressure, which is 1 bar. Next, to calculate the size of the reactor, according to Noor, Key and Chen, we can find the rate of reaction for WGS with the catalyst can be given by negative R equals to K times with the partial pressure of CO. And then we can get K equation from the kinetic data, and with the given K naught and EA, we can calculate the value of K by putting all the information into the equation, and we can get the K value, which is 6.61 times 10 to the power of -4. And from the stoichiometric table that has been presented before, we can get the information of Fc naught and the expansion factor. The expansion factor is 0 because the lambda is equal to 0. And assuming the ideal gas property, which is P equals to CRT, we can make the equation rate law in terms of concentration. And by adding the information of concentration of CH4 from SMR calculation and concentration of CO entering WGS reactor from the stoichiometric table, we can calculate the volume occupied by catalyst, which is 51.95 dm3. And with the volume occupied with the catalyst, we should use at least 62.83 dm3 of total volume of reactor, which is calculated using the formula pi r squared L, with 5 decimeter long and 2 decimeter radius. This volume will be enough to fit the required volume of catalyst and provide excess space for safety measures. So the density of the catalyst, which is 50% of CuO supported by ZnO supported by Al2O3, can be calculated using this equation, and we just insert the density of each, and we will get the density is equals to 5550.5 gram per dm3. And assuming the porosity is 30%, the bulk density for catalyst is also calculated, and we can calculate the total mass of catalyst needed in WGS reactor using the formula density equals to mass over volume, and we can get the mass is 201.84 kilogram.
Now moving on to the separation process 2 part. For this part, we are using a PSA system in this particular model. We've also divided this part into 4 separate parts, which are the comparison between the adsorbents, isotherm of the chosen adsorbent, design of the adsorption column, as well as strategies to obtain 99.9% hydrogen. Now let's start off with the first part, which is the comparison between adsorbents. There will be three different adsorbents used to be compared, which are activated carbon, zeolite 13, and zeolite 5A. Two different methods will be used to compare these adsorbents, which are the properties and its isotherm curves. Let's start off with the properties. The first adsorbent is activated carbon, and it has a porosity of 0.35, a diameter of 0.64 nanometers. And as for the next adsorbent is zeolite 13, which has a porosity of 0.47 and a diameter of 0.87 nanometers. And last but not least, zeolite 5A, which has a porosity of 0.65 and a diameter of 0.5 nanometers. Now moving on to the second method, which is its isotherm curves. In the top left-hand corner, it shows the graph of activated carbon at 25 degrees Celsius. And as you can see, it is not a very defined isothermal curve. Now moving on to the top right-hand corner, shows the isotherm curve of zeolite 13 at 25 degrees Celsius, which is represented by the green line, and again it does not show a very defined isotherm curves. Last but not least shows the graph, the isotherm curve graph of zeolite 5A at 25 degrees Celsius, which is represented by the red line, and it shows the most defined isotherm curve compared to the other three. Based on these few reasons alone, it shows that zeolite 5A is the better and most suitable adsorbent to use in this particular PSA system. Not only because of its very defined isotherm curve, but also because of its properties being better than the other two adsorbents. For example, it has a lower diameter compared to the other two, which means it has the most surface area suitable for adsorption. It also has the higher porosity value, which means it will be better for adsorption. Now moving on to the isotherm of the chosen adsorbent, which is zeolite 5A. First up, the Langmuir isotherm. And the equation used here is Q equals to QMP over K plus P. And its linear equation is shown right below. After plotting the linear equation, we do obtain a straight line for the 1 over Q versus 1 over P graph, which means that zeolite 5A fits the Langmuir isotherm. However, we still should compare with the Freundlich isotherm at the equation of Q equals to Kp to the power of n, and as well as its linear equation shown below. And after plotting the graph of log Q versus log P, we do not obtain a straight line graph, which shows that it does not fit the Freundlich isotherm. Now moving on to the design for the adsorption column. All of the time taken for this particular design is taken from the same breakthrough curve. However, there are different total heights that are taken to ensure the best optimum MTZ can be obtained. To start off, we used a total height of 700 with a TU of 100 and TT of 180. With this, we obtained a total bed height of 3.89 meters or 388.89 centimeters. To find the amount of unused bed, we have to take the total height minus the bed height, which is 700 minus 388.89, which gives us 311.11 or 3.11 meters. And since the unused bed is equal to MTZ, then the MTZ or mass transfer zone is 3.11 meters. Now to alter and modify to obtain a more optimum design, we changed the total height to 500 centimeters, which changed the total height of bed to 2.78 meters or 277.78 centimeters. This also then changed the height of unused bed to 2.222 meters, thus proving that the MTZ is now 2.222 or its optimum MTZ value.
Hi, my name is Hafiszi Ismail, and I'll continue the presentation with the strategy to obtain 99.9% of H2 production and regeneration process. So there are two methods that we use to obtain 99.9% of H2 production. The first method is by using PSA cycle. So as shown in figure 7, the PSA system consists of 6 steps. First, in column A, the feed enters and produces a subsequent product. Meanwhile, in column B, a blowdown occurs. Then, the next step, nothing changes with column A. However, in column B, vacuum is pumped throughout the column. Step 3 involves the production of the feed from column A to act as the new feed for column B. The next steps 4, 5 and 6 are the reverse of step 1, 2 and 3. The constant moving of the feed from different columns causes a swinging motion. Thus is the reason for it to be called PSA unit. Next, let's take a look at the second method to obtain 99.9% of H2 production, which is by using a membrane. This type of technology is known as membrane filter. There are a lot of famous companies that use this type of strategy to obtain 99.9% of H2 production, such as company like Generon. This technology ensures 99.9% of production of hydrogen in PSA system. Besides that, this method also has certain advantages, such as low in heat loss, environmentally friendly, and small footprint. This method begins with the feed gas being cooled down to ensure that the bigger or higher hydrocarbons can be removed before it condenses in the membrane fibers. After the removal, the feed is then heated to ideal operating temperatures. It then enters the membrane filters. Only hydrogen passes through the membrane and thus producing 99.9% of hydrogen. So next, let's move on to the process modeling and simulation part, where we discuss about the mass balance of CO2 separation system. Next, for CO2 separation system, there are two components involved in the system, which is the absorber and desorber. For absorber, there are two inlets, which is the gas inlet where all the gases are coming in, and also the liquid inlet where the liquid solvent coming in, and hence produce two types of product, which is the top product and the bottom product. Next, the bottom product will go into the desorber to produce top product, which we denote as D, and also the bottom product where we denote as B. At the top part of the desorber, there is condenser reflux drum system, while at the bottom part of the desorber, there is reboiler. Next, the bottom product will recycle back to the absorber to ensure maximum of CO2 could be separated from the solution. So, for the absorption part, we calculate the mole fraction of CO2 at the bottom product and we get 0.073 mole. To verify, we calculate the mole ratio of CO2 at the bottom product and we get 0.0622, and the value can be considered equal to the value of x1 that we obtained by using the assumption of equilibrium line. So for the desorption part, after we do the overall mass balance and material balance, we found that by using material balance, the left hand side and right hand side is equal. So we can say that all the values that we are using and we assume are correct. So that's all from us, Group 2E. Thank you very much.